Well, it's always a pleasure to come to Korea. This time especially I've seen many old friends, and I've also met new friends. Okay, so what I want to talk about today is the diffusion, is the interaction between diffusion and spatial heterogeneity. So everything I'm going to talk about is pretty simple stuff. So if you don't follow, just raise your hand, stop me. I will go over that. Okay? All right. I will start with the logistic equation. It's an ODE. U here represents the total population. T is the time. And A is the constant that represents the carrying capacity. That is to say, in each habitat, because of resources are limited, there is always an upper bound for the habitat to support a certain population, certain species. The population has an upper bound. And A represents that carrying capacity of this habitat. So this is a very old equation. In Minnesota, we teach that in second year sophomore calculus. Anyway, so if you put in, one of the first things people do to put in the spatial variable is to assume the diffusion, that the individual is moving around randomly, which is perhaps not realistic, of course, but we'll come to that later. That's more or less the first order approximation. So U now represents the population density at point X at time T. So U is a function of X and T. And this nu represents the unit outer normal on the boundary of omega. Omega is a bounded smooth domain. And the du d nu equals 0 represents there's no flux of the population going through across the boundary. So it's a self-contained, isolated system. And this is Laplacian. So the fundamental fact of this PDE does not differ from the ODE. You see, the ODE, if U is less than A, then U sub T is positive. That means U is going up. If A is bigger than A, that means U sub T is negative. That means U is going down. So U will converge to A. With the PDE, same thing. It's a fact that there's a unique steady state, positive steady state, U identically A, which is globally asymptotically stable. And it's easy to prove using well-known standard upper and lower solution method. In a heterogeneous environment where we assume at point X, the carrying capacity is mx. And m can vary now, no longer a constant, so we're going to assume n explicitly non-constant. And the rest remains the same. Still, we assume random diffusion, random dispersal, and no flux boundary condition. So for this one, the fundamental fact remains the same. That is to say, for every d positive, there is a unique positive steady state. Let's denote it by theta d. And theta d is unique and globally asymptotically stable. So far everything remains the same as before. The proof of this one is a little more complicated, but not much more. We need to deal with eigenvalue problems in order to prove this one. Anyway, what's interesting about the theta d now is that, you see, let me first show you a simple calculation. you observe that, let's say we have a solution. We plug in theta d into the equation. We have d Laplacian. Let me just do it here. It's very simple. D Laplacian theta d plus theta times m minus theta equals 0. You divide through by theta, and you integrate by parts. This one remains there. This one becomes, you throw this is the same as what? D 1 over theta Laplacian theta. So you throw one derivative to the other side. This gives you negative d gradient 1 over theta gradient theta, dot gradient theta. But when you differentiate this, you get another negative sign, so you have d gradient theta square over theta square. That's always positive. The reason is gradient theta is never 0. That is to say, theta is never a constant. Why? Because m is not a constant. Okay, so this is always positive. That means this is always negative. That means we always have integral m is less than integral theta. It's a trivial calculation, but why should I go through that? I just want to make sure you know this is correct. Okay, now let's stop and think about what it means for this formula. Mx is the carrying capacity at x. So integral mx represents the total carrying capacity. That should be the upper bound for the total population. However, this is the population, right? No matter where you start, the inertial value, as long as the inertial value is non-zero, it's going to converge to this theta d because it is globally asymptotically stable. So eventually, the habitat will support this much population. And the total population is integral theta d, which is always bigger than the total carrying capacity, which is supposed to be an upper bound, naively speaking. So there's something wrong here, right? Well, there's nothing wrong. You see, the computation I just went through, there's no mistake. But this turns out to be a very important fact. Anyway, I'll leave it to you as an exercise to figure out why this is the case. As long as d is positive, we always have that. Okay. This will play a very important role in the Lotka-Volterra competition system that I'm going to address to later. But before I go on, let me just go a little bit further to talk about this single equation, the simple fact. One can also show as d goes to 0, theta d goes to m. As d goes to infinity, theta d goes to the average of m, which is very reasonable, right? D is large means the individuals moves very fast. That tends to give you the averaging effect. Therefore, it goes to the average. This means each individual doesn't move so much. Therefore, theta d goes to m. Then, in either case, the integral of theta d goes to integral of m, right? D goes to 0 or infinity. Therefore, in this picture, if the horizontal axis is d, then the integral of theta d as a function of d always lies above this constant integral of m. And on the two ends, 0 and infinity, it is the constant integral of m. In between, it's positive. It's bigger than that. So it is open question that what should this value be, the maximum, and where should this maximum, where is the maximum assumed? Presumably this depends on m, and you can express that. You should be able to express that in terms of m. Such a simple problem, you only have one quantity, that is m. The problem remains open. It's a simple problem, but it's open. So there are so many young people here. You can work on it. It's a lovely little thing one can do. Anyway, so now I want to go to the system. and to talk about one of the consequences of this fact that I'm talking about, that the integral of theta d is bigger than the integral of m for any d. All right. So what I want to talk about now is a system of two competing species. The two species, u and v, are assumed to be identical, except they move at different speed. That is to say, they are identical in competition, they use the same resources, they compete exactly the same way, but D1 is different from D2. They have a different speed of dispersal. They have a different rate of dispersal. Again, no flux boundary condition, and the inertial value is assumed to be non-negative, and I want to say that they are always assumed to be non-zero. Okay? All right. So what happens? It turns out that in 1998, 4 people, Dockery, Hudson, Mishaikov, and Pernarowski, they showed that if D1 is smaller than D2, then UV, no matter what they are, as long as they are non-zero, UV must approach theta D1 0. You see, if V is 0, theta d here, what I was talking about for the single equation, becomes theta d0 is a solution of the system. It's a steady state of the solution. So this means U will always survive, while V will always vanish. That is to say, U will always outcompete V. U will always wipe out V if D1 is less than D2. So this doesn't seem fair, right? The lazy one, U, is more successful. But anyway, it's a fact that proved in 1998, and we're going to try to understand that a little better today. All right, so this is called slower diffuser always prevails. Let me write down the theorem in the mathematical terms. If D1 is less than D2, then theta D1 0 is globally asymptotically stable when 0 theta D2 is unstable. So in particular, there's no coexistence. That is to say, the original system does not have any solution, any steady state U and V. Both are positive. All right. Actually, it's a little more that one can prove. That is to say, you see, if we represented two semi-trivial solutions, 0 theta d2 and theta d1 0, on the phase plane, then one can actually show there's a connecting orbit from the unstable one to the stable one, because this system is actually an order preserving system, a monotone flow, a monotone system. The existence of such a connecting orbit decides all the dynamics. Everything can be done by comparison once you have this connecting orbit. So I'm not going to go into the details of that. It is interesting to point out that if we have 3 or more competing species involved, all identical except their dispersal rates. Let's say we have 3, D1, D2, D3. U, V, W, with dispersal rates at D1, D2, D3. And D1 is smaller than D2, D2 is smaller than D3, otherwise they are identical. Then it is not known if the slowest one, U, would prevail. The reason is that we need to look at the proofs of this fact, but we're not going to go into that. I'm just going to give an outline, or sort of a sketch. The proof consists of 2 steps. The first step, the together is the first step. Okay. The first part of the first step is a local thing, to show that theta d1 0 is stable, while 0 theta d2 is unstable. That's a linearized analysis. Part two of step 1 is to show that there is no other non-negative steady state than 0, 0. So this part actually works for 3 species or n species. Doesn't depend on n equal 2. It's the second step. The second step, we need to conclude from the theory of monotone flow. As I said, this is an order-preserving system, that theta d10 is globally asymptotically stable. This requires n equal 2. So we are now going to, these 2 facts, they don't look, I mean, there are 2 facts we talked about. One is the slower diffuser must prevail. The other one is this total population versus total carrying capacity for single equations. They don't look connected, but we're going to connect them in our approach to understand these facts. All right. We're going to use a more general competition system. This is the classical Lotka-Volterra competition system in homogeneous environment. That is to say, instead of M1, M2, we assume it's A1, A2, and A1, A2 are constant. So I want to provide you with some background of this model. So A1, A2, B1, B2, C1, C2 are all constants. The 2 interesting coefficients are C1 and B2. C1 represents the competition ability of V versus U, while B2 represents the competition ability of U versus V. So we call B2C1 interspecific competition, while B1C2 are intraspecific competition, and so on and so forth. They are all assumed to be positive constants. So now you see, if B2 and C1 are small, that means the competition is weak. Right? And when B2, C1 are small, then we have B1 over B2 is large, C1 over C2 is small. So this is generally the case. We say it's a weak competition if B1 over B2 is bigger than A1 over A2, bigger than C1 over C2. And in this case, the dynamics of that competition system in homogeneous environment is particularly simple. In this case, actually, there are 4 constant steady states only. They're all constants. There are no non-trivial constants anymore. 0, no non-trivial steady states. 0, 0, A1 over B1, 0, 0, A2 over B2 over C2, and U star V star. That's this one. These 2 lines are the 2 null lines of that system. Okay. And one can show that this U star V star is globally asymptotically stable. In particular, no non-trivial coexistence steady state. And this can be proved by Lyapunov functional in this approach. In this, it is usually, to me, it works like a miracle when you can find the Lyapunov functional. But how to find the Lyapunov functional is always an art. So I'm not going to go into that. But it's been proved. We have known that fact since late 70s. So now let's go to the heterogeneous environment. That is to say, A1, A2 are no longer constants. We replace them by M1 and M2, depending on X. Otherwise, the system remains the same as before. We just replace A1, A2 by M1 and M2. Well, M1 and M2 are assumed just as like before, non-negative and non-constant. But we will only discuss the weak competition case. But in this case, we require that B1 over B2 is bigger than M1 over M2 for every X in omega bar is bigger than C1 over C2. Okay? It's a strong assumption, meaning this is a very special case. But even this very special case, we will be able to do something to help us understand the slower diffuser always prevails. All right. So I want to first provide you some background of this heterogeneous environment case. Recall that in this case, in the constant coefficient case, U star V star is globally asymptotically stable, regardless of D1, D2. For any D1, D2, this is globally asymptotically stable. Okay? While the other two semi-trivial steady states are unstable, of course. Okay. Keeping that in mind, now we go to the heterogeneous case. In the heterogeneous case, it is different. But so far, for this one, it is still the same. I'm going to first give you the same conclusions. That is, if both D1, D2 large, then there is a unique steady state which is globally asymptotically stable. Now we cannot write it down because it's M1x, M2x. No longer A1, A2, no longer constants. However, the steady state does tend to this one. What is this one? This one is the U star V star if you replace M1, M2 by M1 average and M2 average. These are constants. So what this means is that although we cannot write down this unique steady state, which is globally asymptotically stable, it does converge to the one it should be. Okay? So there's no surprising here. This was never published. This was communicated by Yuan Lao to me. The proof is highly non-trivial to me. The proof is very interesting, different from the constant coefficient case. Because constant coefficient case, just Lyapunov functional, that's it. This one, the proof is actually a little hard. It goes as follows. First, you show theta D1, 0. Remember, there are two semi-trivial solutions, theta D1, 0, and 0 theta D2. So the first step is to show both are unstable. Then, the monotone flow theory, because this is still an order-preserving system, monotone flow theory guarantees us there is at least one stable coexistence steady state in between. Could be more than one. So that's the first step. The second step, Yuan Lao showed that every coexistence steady state, that is every positive steady state, both components are positive, must be stable. Every one of them stable. Therefore, you cannot have more than one. Because if you have more than one, again, the theory of monotone flow will guarantee there will be one, between two stable ones, there should be one unstable in between. And that gives you a contradiction. But anyway, the proof was never published. All right, so that's that. Now, what happens when D1, D2 both are small? Again, similar. There is a unique steady state which is globally asymptotically stable and tend to the one it should be. This is the solution that behaves at each point, point-wise, just like that U star V star in the constant case. There's nothing special. Okay. Again, the proof of this one is a little more complicated than that. And it was published in Journal of Differential Equations by Hudson, Low, and Mishaikov in 2005. So far, everything is similar. Now we're going to move on to something not so similar. All right. So here's I just want to sum up what we have done so far. The blue region represents that there is a unique coexistence steady state which is globally asymptotically stable. Okay. Now, for the remaining case, when D1, D2 are not small and not large, the situation is drastically different from its counterpart in the constant coefficient case. And here, we're going to take a special case. We're going to assume the coefficient here is 1, coefficient here is 1, which is not any special assumption. There's no problem. But a special assumption here is that M1 equals M2. You don't have to assume M1 equals M2. But the proof gets the statement gets a little more complicated. So I want to use this one as an example. So M1 equals M2. What happens to this system? In this case, because M1 equals M2, the weak condition for the weak competition becomes 1 over B is bigger than 1 is bigger than C. That's the weak competition condition. All right, so here's the theorem proved by Yuan Lo in 2006. He showed that if M1 equals M2, then there is a B star, which is smaller than 1. For any B between B star and 1, there is a C star, a small number, positive number. That is, for any C smaller than C star, theta D1 0 is globally asymptotically stable for some D1 D2. What does that mean? That means if the competition ability of U versus V is strong. Strong means, well, not strong, but stronger. Stronger doesn't mean strong. Okay, stronger. That is closer to 1, while the competition ability of V versus U is weaker, that is close to 0, then, but still we are in the weak competition case, then U will wipe out V for some D1, D2, for some D1 less than D2. Maybe not all, but for some D1 less than D2, actually not all. So this is different from the constant coefficient case already, because in the constant coefficient case, this never happens. For any D1, D2, the U star V star is globally asymptotically stable. Okay, so now the B star here is very interesting, and we are going to look at this B star now. So B star is given by this number. So what is this number? Remember, we have proved here that theta D is bigger than, integral of theta D is bigger than integral of M. So if we look at M over integral of theta D, or theta D1 in this case, this is always less than 1. Now, but in the two ends, 0 and infinity, it's always 1. So you can take the minimum over D1. Okay. If you take minimum over D1, this is going to be a number strictly smaller than 1. And that is the B star here. Okay? All right. So this relates the integral. So the total population is important. Actually, there are two things important in this approach. Total population is one of them. There's another one. We'll come to that later. That is the distribution of theta D1 versus M. That's also important. But anyway, we'll come to that later. So B star is less than 1 is given by this one. Okay, but in any case, Yuan Lo's theorem guarantees that for some D1, for some BC between 0 and 1, where B is closer to 1, C is closer to 0, and for some D1, D2, some D1 less than D2, U will wipe out V. Coexistence is no longer possible. And this wipeout means for any inertial value, that is, any inertial value, no matter how small the population of U is to begin with, U will eventually prevail. So that's the meaning of this one. So this is quite different from before. But why is this related to what the slower diffuser must prevail? It's not so clear. So we're gonna continue talking about that. All right. Anyway, one of the things here that if one can criticize the theorem at this time, that must be that one can say, okay, your B is closer to 1, your C is closer to 0, meaning the competition ability of U versus V is stronger than the competition ability of V versus U. So then you say the result may not be so strange, may not be so striking. Anyway, so I want to talk about some recent progress I did with my student, Lam. So we also consider the same system, but we just take the elliptic system out. Then one can show that. Then we can show that for any epsilon, there is a delta, such that if B gets into closer to 1, well, C can be 1. So the interesting thing here is that C actually can be bigger than B and can be 1. Then for any D1 between epsilon and 1 over epsilon, and for any D2 bigger than or equal to D1 plus epsilon, U wipes out V. Okay. But given that, I will draw a picture later, but I want to present the second result, which is in some sense complementary to this, which complements this result. That is, so in here we are talking about given epsilon, and we vary BC, right? BC varies. Here we are talking about fixed BC. Then there is an epsilon positive such that if D1 and D2, the difference is less than epsilon, then there is a unique positive steady state U tilde V tilde, which is globally asymptotically stable. And as D1, D2 converge to, if they converge to the same value D, then we also know what this one looks like. So basically, these two results says that if D2 is bigger than D1 plus epsilon, with B in this range, we have U wipes out V. Well, if D1, D2, with D1 is not bigger, well, or say for any fixed BC, there's an epsilon such that if D1, D2 are the difference between the two are smaller than epsilon, then there's coexistence. Not only there's coexistence, there's always coexist. So globally asymptotically stable is different from locally asymptotic stable. Globally asymptotic stable means no matter what inertial value you start with, they always coexist. Okay, so let me draw pictures now. So this is for local stability. I just want to ask, sorry, Youngjun, is it 50 minutes? Right, okay. So the local stability of theta D10 for B bigger than B star. So this is what Yuan Lou's, I didn't prove this one, I didn't show this one, but this is what in Yuan Lou's paper, he showed this one. Okay, so the yellow region represents that theta D10 is locally asymptotically stable. And there are two global stability for theta D10. That is for U wipes out V. That one is that C is small, the other one is C is large, but B has to be large. Here C is small, C is small, but B doesn't have to be too large. B is just bigger than that. So let's draw the picture here. So this was the picture I just showed you. And I'm going to use the red region. So the yellow region represents the local stability. The red region represents the global stability. But here, of course, one needs to add that C small in order to have global stability. All right. Now, putting the two together, the global for the globally asymptotically stable coexistence steady state, and its counterpart, we have this picture. So this is the case when B is close to 1, smaller than 1 but close to 1. C is arbitrary, can be 1 or smaller. Yellow region represents that theta D1 represents U wipes out V, locally. The theta D10 is locally stable. This is globally stable, U wipes out V. And I will use blue region to represent the coexistence, global coexistence. So this region was proved by Hudson, Low, and Mishaikov. This is proved by Low. And what we did was we connected the two along the diagonal. So everything on the blue region, we have we have a coexistence steady state which is globally asymptotically stable. On the red region, is the opposite. Sorry. Of course, we don't know everything in between. All right. So that's roughly is the situation up to this point, and maybe I will skip the proofs. Okay, it's a small point, but maybe I will skip that too. Actually, if you look at the result there's a uniformity in the result. But I do want to mention some open problem at this time. Again, so one of the open problems is that is it possible that theta d1, 0, is locally stable but not globally stable? So far, we have no examples for this to happen yet. Presumably, it could happen, but we don't know. All right, so the rest are... Now, what happens when B is smaller than B star? B star is this number. If B is bigger than B star, we know theta d1, 0 is locally stable. If B is smaller than that, of course, it is unstable. But what happens to the rest of the... So both semi-trivial steady states are locally unstable, but depending on d1, d2, one can say what happens and so on and so forth. The situation is not clear, but I think I will skip over that, skip over this one to go into the directed movement. This approach is, so in reality, one suppose that few species will move completely randomly. It is plausible that diffusion combined with directed movement will help the species to survive. But anyway, here is what Cantrell, Kastner, and Yuanlou in 2006 proposed to do based on an earlier single equation model of Belgason and Kastner. What they assume is that, you see, this system differs from the previous one that we have considered only in the blue part. We added the blue terms here and the blue terms here. Or rather, they added the blue terms here and here. So what does that mean? What does this blue term mean? It means alpha is positive. It means that U moves up the gradient of M. So in some sense, that in their words, they are assuming U is more intelligent. You can move up the gradient. You can move toward a better environment. That is the gradient, in the direction of gradient M. And naturally, if you assume that that's the case, then this is the flux now. So the no flux boundary condition becomes this one. So once you add that, this term is automatic. It should be added here. Otherwise, it's inconsistent. Okay. Otherwise, it's not a no flux boundary condition anymore. All right. So that's what I just said. Now, when D1 is less than D2, we know the slower diffuser U always wipes out V when alpha is 0. They also show that when alpha is small, this is the case. Okay. Now, they also show that that V always survives when U becomes too smart, meaning when alpha becomes too large, V always survives. Or put it this way, U will never wipe out V. So the theorem is the following. This is the crucial assumption they make, is that the critical points of M has measure 0. So in particular, this rules out the case when M is a constant on a set of positive measure, on any subset, let's say, or not subset, on any, sub-region of omega. They also assume, this may be technical, so the assumption A is important, assumption B may be a technical one, I don't know. The assumption B says that the global maximum has to be a strict local maximum. Okay. In some sense, this is fairly consistent with the spirit of this assumption too. Then they show for all D1, D2, the system has a stable coexistence steady state, U alpha, V alpha, for both are positive, of course, for every alpha large. They can show that. But they only show, here what I said was a stable coexistence steady state. This conclusion does not imply what I just said here. U always survives when alpha is large. But this is just one example of the results they show. One result they show. But they actually show this one. The conclusion contains the statement. So anyway, what happens to the shape of U alpha, V alpha? That is the distribution of U alpha, V alpha. As I said earlier, there are two things important. One is the total population, theta D1, which we have seen already. Second is the distribution of U alpha, V alpha. This one we haven't seen how important that is yet, but we'll get to that. Okay. So here is what they showed. When alpha is 0, D1 is less than D2, U wipes out V, meaning eventually the population of V goes to 0. But when alpha is large, Cantrell, Kostner, and Yuan Lo showed that if the critical points of M is of measure 0, then the U alpha, V alpha may not be unique, but for any U alpha, V alpha, U alpha will always go to 0 in L2. So in particular, U alpha will go to 0 in L1. But this convergence is in alpha, steady state, not in T, in alpha. That is to say, U alpha will survive for any alpha large, but the population of U alpha will go down to 0. It will become smaller and smaller if alpha becomes larger and larger. So that's what it says. And V alpha will converge to theta D2 as alpha goes to infinity. So this means V alpha will behave just as if U alpha does not exist. In other words, V alpha will behave as if there's no competition if alpha is large. So in some sense, this is I think this is very interesting, may not be totally reasonable, and one has to modify the assumption. That's what mathematics could do to those models. Anyway, and they also made a conjecture. The conjecture was the following. This conjecture is about the shape of the U alpha, V alpha. They conjecture that one, that is the system, has a unique coexistence steady state U alpha, V alpha, which is globally asymptotically stable. So they conjecture it's unique because we have the existence already. They conjecture it's a unique and it's globally asymptotically stable. Moreover, U alpha will concentrate at all local maximum points of mx in omega bar, in the closure of omega. So this is this is a conjecture on the shape of U alpha. Well, V alpha, we know that already. V alpha goes to theta D2. There's no conjecture is necessary, of course. All right. Xin-Fu Chen and Yuan Lo in 2008 made an important progress on this conjecture. When M has a unique non-degenerate global maximum point. Well, actually, they also need a little bit more assumption on the boundary. That is to say, the normal derivative of M on the boundary must be less than or equal to 0. And M has a unique critical point x0, which is a global, non-degenerate global maximum point. Then they can show the solution U alpha will approach a Gaussian. The first part is sure we know that. Now the second one is U alpha times this one. This is a Gaussian, right? D2 mx naught this is a symmetric matrix, and positive definite because this is a non-degenerate global maximum, or negative definite. And so if you divide this one over here, this is the value, mx0 minus theta d2x0 times 2 to the n over 2, this value. This is the amplitude of the spike of u alpha. And the shape of the spike is this amplitude times the inverse of this Gaussian. Okay. So that's the shape of u alpha. And in some sense, this verifies the conjecture in the special case. I want to explain just a little bit about how this constant comes about. This constant comes from the integration of the equation. You first integrate the equation, you get the following. You get this one equals 0. And if you also know u alpha is Gaussian like this, you just plug that in here. You see, you will have u alpha squared and u alpha v alpha here and m here. And this becomes, so the coefficient in front of u alpha is m minus v alpha. And that contributes mx naught minus v alpha x naught, which is theta d2 x naught, because v alpha goes to theta d2. The other one is u alpha squared, right? So you will get m minus vx naught u alpha equals, the integral of that equals u alpha squared. And if you plug this Gaussian in there and compute, this constant comes out, 2 to the n over 2. And that's where this comes from. Anyway, I also want to report some recent progress on this one. This was, in n equal 1, this was completely, in some sense, completely solved. And our theorem is that, again, we are assuming all local maximum, all critical points are non-degenerate, but it could be more than one now, and it could have a local, of course, a local minimum. And this assumption is the same as the normal derivative of m on the boundary is non-positive. Then for any u alpha v alpha, one has the same profile as before, except now this one is no longer always positive. Sometimes this is actually negative. And the u alpha goes to 0 everywhere and uniformly exponentially away from those peaks. All right. So the conjecture of Cantrell, Kastner, and Yuanlou needs to be modified slightly. I will use a picture to show you. So suppose this is the mx. Then this would be the theta d2 for v. And you notice that theta d2 is bigger than m at this local maximum point. So the local maximum point of m has 3 points. But this one is underneath, is below theta d2, and that would be below v, because v goes to theta d2. So you will focus on only the 2 points here, not on this one. Therefore, initially, u alpha near this point will move towards this point and eventually gets eliminated. So this serves as a trap for u alpha in this range. All right, so my time, I have 1 more minute. My time is almost up. All right, u alpha will not survive at those local maximum points when m is less than or equal to theta d2. So that's what I just said. I'm not going to use, the proof it uses very elementary arguments, but very different from what Yuanlou and the Xingfu Chen did. For higher dimensional case, it has been done by Lam, who's my student, and so I will not go over that. I would just say the higher dimensional case was done. And I will now jump onto the last page of this of this talk, I would say, and go into, because the higher dimensional case is much more difficult. I would just talk about a slightly different model than what we just did. So what we did here was we replaced the gradient m by gradient m minus u, because this is not what we did. This is Cantrell, Costner, and Yuan Low in 2009 they did, because this will take into the crowding effect. If near a local maximum point of m, you aggregates too much, then the force gets smaller. So in some sense, this measures the fitness of the location. And this would be a very desirable model to try out as a next step. In general, what would be the best strategy for survival or competition? You will have a system of this kind where for you, this is the competition, and this is you would follow. You would follow the competition wherever the competition that it is most successful. You will follow that. While V will take a different strategy. This is still the competition, but V will take a different strategy, F tilde gradient. So this would be a general thing that one tries to work on. But what would be the best strategy? Meaning, how do you choose F tilde versus F? Now, all what I said so far does not include cross-diffusion model, which was proposed in 1979. So maybe there's a way to incorporate that into here as well, but so far there has no result in this direction. So I think this is my last page. Thank you for your attention.